Hello, students. Have you ever shouted in an empty room or a big hall and heard your own voice bounce back? That's reflection of sound in action. Just like light, sound waves too can return back into the same medium when they strike a hard surface. The proper definition is this: the return of a sound wave from a surface back into the same medium is called reflection of sound. It happens with walls, plywood, or even a metal sheet, and the best part is, it doesn't need a shiny mirror-like surface like light does. So next time you clap in a corridor, you're really just experimenting with sound reflection. Now, just like light, sound follows the two golden laws of reflection. First, the angle of incidence equals the angle of reflection. That means if the sound wave comes in at 30 degrees, it bounces back at 30 degrees. Second, the incident ray, the reflected ray, and the normal all lie in one plane. These rules are universal and work whether you are whispering softly or playing music loudly. As you can see in the diagram, the incoming ray and the outgoing ray behave like obedient students following the rules of geometry. Unlike light, which needs a smooth and shiny mirror, sound waves are less demanding. They reflect from almost any hard surface, whether smooth or rough. So walls, metal sheets, or even wooden boards can reflect sound. The real deciding factor isn't how polished the surface is, but how big it is. Think of it this way: sound is less picky than light. It doesn't need a mirror finish, just a good solid surface to bounce off. Here comes the important condition for sound reflection: the size of the reflecting surface must be bigger than the wavelength of the sound wave. Now remember, wavelength is equal to velocity divided by frequency. Since the speed of sound in air is about 340 meters per second, audible frequencies from 20 Hz to 20,000 Hz give wavelengths between about 17 meters and 1.7 centimeters. That's why everyday surfaces like walls or boards easily reflect sound, because they're much larger than these wavelengths. So the takeaway: small objects don't reflect sound effectively. Your notebook won't act like a sound mirror, but a wall will. Reflection of sound isn't just a cool phenomenon, it has real-world uses. Take a megaphone or speaking tube. It reflects and directs sound waves in one direction, making your voice louder to a distant audience. In auditoriums, sound boards are placed behind speakers so that sound reflects towards the crowd evenly. And your trumpets, once used by people with weak hearing, work on the same principle, collecting and directing sound into the ear. So the next time you use a loudspeaker at a school function, remember, you're really harnessing the power of sound reflection. Let's put this into numbers. Suppose we have a sound wave of frequency 500 Hz traveling through air at 340 meters per second. The wavelength is given by lambda equals velocity divided by frequency. That's 340 divided by 500, which comes out to 0.68 meters. The rule says the reflecting surface must be bigger than the wavelength, so in this case the surface should be larger than 0.68 meters. That means a large board or wall will reflect the sound, but something smaller like a notebook will not. So always compare wavelength with surface size before deciding whether reflection will happen strongly. So, let's wrap this up. Reflection of sound is simply the bouncing back of waves into the same medium from a hard surface. It follows the same rules as light: angle of incidence equals angle of reflection, and all rays lie in a plane. Any hard surface can reflect sound, but it must be bigger than the wavelength. And finally, reflection has countless applications: megaphones, sound boards, and even ear trumpets. In short, reflection of sound is not just theory, it's all around us in daily life, amplifying voices, directing sound, and helping us hear better. See you in the next session with more amazing physics concepts.